Welcome to this explainer. Today, we're treating the history of the atom like a giant, fascinating generational puzzle. We're going to upgrade our understanding all the way from atom model 1.0 to 5.0, and then we're handing the baton straight to you. Think about it for a second. An atom is completely invisible to the naked eye. So how in the world do you figure out what's inside a locked box without ever actually opening it? Well, that is exactly the detective story we're diving into today. We're going to explore how brilliant minds use some truly incredible clues to map out an invisible world.
All right, here's our quick roadmap for the day. First up, understanding the atomic model. Then, early spheres and puddings, followed by discovering the nucleus. After that, we'll get into orbits and quantum clouds. And finally, we'll wrap up with build your own atom.
Let's jump right in. Section 1. Understanding the atomic model.
So the absolutely crucial point to start with here is that an atomic model is really just a helpful visual tool. Scientists use it to map out the microscopic structure of matter. Because, atoms are far too small to ever see, we have to rely on these visual representations to wrap our heads around how their parts are arranged. And this is exactly why models matter so much in science. When we literally can't observe something directly, a model lets us test complex theories, predict how elements are going to react, and visualize the really intense mathematics happening behind the scenes.
It's kind of like a massive software update. Our scientific understanding evolved over time through these 5 distinct eras, all because new technology provided new clues. We didn't just magically jump straight to modern quantum physics, right? It took generations of scientists refining and honestly sometimes completely destroying each other's work to get from that first solid sphere to the modern electron cloud. Each era is a massive paradigm shift. Old textbooks basically had to be thrown out and rewritten from scratch. It just goes to show that the scientific process is deeply iterative. We build on past mistakes to finally uncover the truth.
Moving right along to Section 2, Early Spheres and Puddings.
John Dalton kicks things off in the early 1800s with a surprisingly simple but totally foundational idea. He thought atoms were tiny, indestructible, solid balls, very much like billiard balls just clacking and combining together to make different compounds. He believed matter was made of these featureless spheres that chemically locked together to form literally the entire world around us. Now, in an era way before advanced technology, just proposing that invisible, unbreakable units made up everything we touch, well, that was a truly revolutionary starting point for chemistry. It finally gave scientists a solid baseline to work from, even if the detective story was just getting started.
Fast forward a few decades, and J.J. Thomson comes along with his famous cathode ray tube experiment. He discovers the electron, which effectively shatters Dalton's unbreakable billiard ball. Thomson updated the whole model to feature negatively charged particles swimming around in a positively charged sea. Now, he called it the plum pudding model, but honestly, let's use a more modern analogy. Imagine a freshly baked chocolate chip cookie. The warm, positive dough is the atom itself, and the chocolate chips? Those are the negative electrons scattered evenly throughout. Suddenly, the atom isn't just a solid ball anymore, it actually has pieces inside it.
Notice the huge shift here. We went from Dalton's completely solid, indestructible ball to Thomson's much more complex mixture of positive and negative subatomic pieces. So why does this matter so much? Because it definitively proved that the atom wasn't the smallest particle in the universe after all. Finding subcomponents hiding inside what was thought to be an indivisible unit, that was an absolute mind-blowing revelation at the time. It basically fired the starting gun on a massive race to figure out what else might be hiding inside the atom.
Which brings us to Section 3, Discovering the Nucleus.
Enter Ernest Rutherford. His famous gold foil experiment forced yet another massive update. So Rutherford shoots these tiny alpha particles at an incredibly thin sheet of gold foil. He fully expected the particles to just pass right through Thomson's soft positive cookie dough. But instead, well, almost did go through, some particles ricocheted violently backward. Rutherford famously said it was like firing a massive artillery shell at a piece of tissue paper and having it bounce back and hit you in the face. Crazy, right? That profound shock proved Thomson wrong. The atom actually had an incredibly tiny, super dense, positively charged core right in the dead center. We call that the nucleus now, and those electrons, they're just orbiting far away.
Next up, Section 4, Orbits and Quantum Clouds.
Then, Niels Bohr takes us straight to the stars with his planetary model. He argued that electrons travel in very defined circular orbits, or fixed energy shells, around that newly discovered dense nucleus. When you look at elements like oxygen and silver, you can clearly see how atoms get more complex.
Oxygen has just a few little electron planets tracing neat organized circles. Silver, on the other hand, is a lot larger. It has way more electrons organized in strict outer traffic lanes, very much like planets reliably orbiting the Sun. But wait, the modern electron cloud model, championed by Erwin Schrödinger, comes in and changes everything all over again. He showed that electrons actually don't move in neat, predictable rings at all. Instead of a train on a fixed track, you got to think of an electron more like a wild swarm of bees buzzing around a hive. You don't know exactly where any single bee is at any given millisecond, but you do know the general area where they're most likely to be hanging out. So we get this incredible visual of a probability map. The quantum cloud is just much denser wherever the electron is highly likely to be found.
The shift from Bohr's neat fixed circles to the complex, scattered probability clouds is pretty much the culmination of our historical journey. Moving from absolute certainty into complex probability literally marks the birth of quantum mechanics. It's a completely new way of viewing reality at the microscopic level. We are officially abandoning those predictable solar systems for a much more dynamic and frankly mysterious quantum world.
All right, let's get to the fun part. Section 5. Build your own atom. Now that you've seen the history, it is your turn. It's time to step right into the shoes of these historical detectives and become a young scientist yourself. You are inheriting the legacy of Dalton, Thomson, Rutherford, and Bohr. So here is your 5-step workflow for the Atomic Model Project. First, you'll pick your proponent, deciding which era of history fascinates you the most. Second, you'll dive deep and really research their main ideas. Step 3, and this is the best part, engineering a physical 3D model. Then you'll put together a sharp visual infographic guide. And finally, you're going to confidently present your findings to your classmates.
Now, a vital requirement for this physical build is that you absolutely must be eco-friendly. We want to see you transform everyday waste into a total scientific masterpiece using only recyclable materials. Seriously, think cardboard, toilet paper rolls, bottle caps, old egg cartons, even newspaper. It's all about being incredibly resourceful. Use that creativity to showcase complex physics, all while doing your part to save our planet. Of course, as you get resourceful gathering all those materials, safety is paramount. Definitely avoid sharp or dangerous objects, but I really want to emphasize that last point. Cooperating with your group mates. Look, teamwork is a core scientific principle. Rutherford, Bohr, Schrödinger, none of them worked in total isolation. They debated, they collaborated, and they built on each other's wild ideas in crowded laboratories. Your ability to communicate and build together is honestly just as crucial to a successful experiment as the actual cardboard and glue you're using.
When you review the submission checklist and scoring rubric, you're going to notice that the heavy focus is placed on scientific accuracy, your visual guide, and that essential teamwork we literally just talked about. If you really want to elevate a satisfactory project into that top-tier excellent range of 25 to 28 points, you've got to pay attention to the details. Make sure your physical model is durable and neat. Ensure your written explanation clearly covers both the strengths and the limitations of your chosen era. And please, guarantee that every single member of your group participates equally.
So, as you kick off your project and prep for your presentation, I want to leave you with this final thought to chew on. Why is the specific model you chose actually important in the ongoing, ever-evolving detective story of the atom? Consider what major breakthrough it offered and also what limits it eventually hit. Your physical model is basically a snapshot of how ideas have grown over time. The quantum model is era 5, sure, but science never stops. Maybe one day, one of you will help design era 6. Be a young scientist, think, create, and inspire. Thanks for joining me for this explainer.